Let us take an example of how to design an impedance matching circuit to match a certain load impedance to a certain source impedance. In this particular example, we are using the Smith chart to match a certain source impedance of 150 plus j 75 ohms plus j 75 ohms to a certain load impedance of 75 plus j 15 ohms at a particular frequency of 2 gigahertz. We are looking at the topology of the LC circuit as, let's say, is already given to us. For example, let's say we want to design a low pass filter. Later we will see that we can design many other topologies as well. This is not necessarily the only topology that we need to design, but to start with, to understand how to use a Smith chart for impedance matching, let us start with looking at this low pass configuration. How do we know it is a low pass filter? Once you have a series inductor, the reactance is going to be increasing with frequency, so high frequency components are going to be cut off, and 1 over j omega c is going to be a short circuit at high frequency, so it is going to bypass the high frequency components. So it's not going to allow, this particular matching network is not going to allow high frequency components to pass through. It will only allow low frequencies to pass through. That's why it's a low pass filter. So to do that, we have been given the source impedance and the load impedance. There are two different ways at least to do that. Either we can start from the source impedance or the load impedance when we design the matching network using the Smith chart. Let's say we want to start from the source impedance side. Let's see that how this particular configuration is able to achieve impedance matching, which essentially means that whatever my load impedance is, my source impedance must be equal to my load impedance, the conjugate of the load impedance. I have to be able to transform my source impedance to the conjugate of the load impedance. This particular example, as the figure indicates, maybe the load could be an antenna, which is a one-port device having 75 plus j 15 ohms. So the conjugate of the load impedance is going to be 75 minus j 15 ohms. 75 minus j 15 ohms. So conjugate, you are simply replacing the j by minus j. To do that, how do we go about using the Smith chart? How do we go about doing that? The first and foremost thing is to take a reference impedance to normalize the given impedances, so that we are able to identify that particular point in the Smith chart. Since you notice that in this particular example, the source impedance is 150 plus j 75 and the ZL is 75 plus j 15, we decide to use a characteristic impedance or a normalizing impedance of 75 ohms. We could use 50 ohms as well. The procedure is still the same. The choice of the normalization impedance is up to us, because we are going to recover back the impedance and admittance values by denormalizing it back with the same reference impedance that we used to obtain the normalized impedance in the first place. Since 150 is a multiple of 75, so is 75 here and so is 75 here, it might be easier to just simply use 75 as the normalization impedance. But we could use 50 as well, and the results will be still the same. The final results will still be the same. Now that we have 75 ohms as the normalization impedance, let's see how does that transform the load impedance of 75 plus j 15. The normalized impedance is going to be 1 plus j 0.2. Now, for maximum power transfer, we want to match the source impedance to the conjugate of the load impedance, and that becomes 1 minus j 0.2. Similarly, the normalized source impedance is going to be 2 plus j1. 150 over 75 is 2, and j75 becomes the plus j1 when you normalize that. If you notice, let us draw the source impedance in the Smith chart. we are going to look at a resistance, a constant resistance curve of 2, which is essentially this particular circle, because it is cutting the Smith chart, the Z chart at 2, at a constant resistance of 2, and the reactance is 1. That means we need to identify that particular point in the Smith chart where the reactance is 1, which is this particular point here. So the intersection of that constant reactance curve and the constant resistance curve is going to give us the value of Zs. Now let us plot the ZL value that we want to have, which is 1 plus j 0.2. Since the real part is 1, we are looking at a constant resistance curve of R equal to 1, a constant resistance curve of R equal to 1. It intersects the Smith chart at this point, which is R equal to 1, and the reactance is 0.2, which is essentially this point here, which is the red value, which is what the impedance chart is about. So the 0.2 value is here, so that is going to be the constant reactance curve, and the intersection of the resistance and the reactance curve is going to be the ZL point. Now to obtain the ZL conjugate, interestingly enough, it is the mirror image of this ZL in the Smith chart. It's the mirror image where the mirror is placed along the x-axis, because when you take the conjugate, the resistance remains the same, the reactance simply becomes the negative of the other. The reactance becomes the negative of other. By positive reactance is going to be correspondingly the same negative reactance, so the mirror image of this point is going to be here. Other way of looking at it is, since resistance is still 1, it is along the resistance curve of R equal to 1, but the reactance is minus j 0.2, which is this guy over here. So we are seeing the intersection of this resistance curve and the reactance curve, and we get that particular point there. That is the ZL star, the conjugate of the load impedance, and this is the source impedance. So what remains in designing the impedance matching circuit is to move this load impedance, this source impedance, to the conjugate of the load impedance by either using a low pass filter configuration like this, or any possible L and C combination connected in series or in parallel. So we decide to choose this impedance matching circuit starting from the source impedance. We can do it the same way by starting it from the load impedance as well. But as an example, let's start from the source impedance side. Now, in this particular configuration, from the source impedance, we see that the first element that is connected to the source in the matching network is a shunt capacitor. We are connecting a shunt capacitor, and following the shunt capacitor, we are connecting a series inductor. So if I were to start from the source impedance, I am connecting an element in the shunt configuration in parallel. So the chart that I should naturally be looking at is the admittance chart. So all I do then is, by adding any shunt element, either a L or a C, I'm just going to move this particular point along the constant conductance curve. That means it makes sense for me to draw this blue curve, which is the constant conductance curve that passes through the source impedance, the normalized source impedance Zs. At the load end, from the load end, we are looking at a series connection of either a L or a C. In this case, it turns out to be a L. That means, as far as my load is concerned, I'm going to be drawing, and the L and the C that I connect in series is going to change only the reactance and not the resistance. So along the ZL conjugate or ZL, doesn't matter, we are going to draw that particular curve with constant resistance, because since it's connected in series, we are looking at the Z chart, the impedance chart, and the constant resistance curve is going to be looking like this. So we draw a constant conductance circle along ZS because the first element that is connected in the source is a shunt element. So that is why we choose the constant conductance, and the element that is connected to the load is going to be in series, and that's why we choose the constant resistance curve, the Z chart, for plotting that. Turns out that we see that there are two intersection points here, and there are two different possible configurations of impedance matching circuit, which is corresponding to the two intersection points. Depending on the number of intersection points you will have as many possible configurations for the impedance matching circuit. This particular configuration is one of the two different configurations that are possible. Let us see which configuration it is, and later we will see what is the other point, the configuration for the other point. So for this low pass solution, starting from the source impedance, the first element that we connect is a capacitor in parallel. We see that a capacitor has a positive susceptance, so that in the Smith chart we are going, in the admittance chart we are going to the lower half. That means we are moving in the clockwise direction, where the susceptance keeps increasing. And how long do we move, or how far do we move? We move to that point where that intersection point happens. That means we move till the point of the constant resistance curve is equal to 1, because we know that this ZL star, the conjugate of the load impedance, is along the constant resistance R equal to 1 curve. So we move that far to reach that particular intersection point. And to be able to move that, we are moving along the constant conductance curve, changing only the susceptance, and we have changed the susceptance value by j omega C2. By j omega C2. As a next step, once we hit that particular intersection point, at that particular point we can know what is the impedance as well as the admittance at that transition point when we connect the shunt capacitor in parallel to the source impedance. We are moving the source impedance to that particular point. As a next element that we connect, this is the target point that we have, so we need to go to that target point, and since we have already plotted the constant resistance curve, earlier because of this series L, we are going to move along that constant resistance curve to that load impedance by this factor. By connecting a series L, the resistance remains the same, but what changes is the reactance, and the reactance is increasing. So we are going in the clockwise direction in the Z chart. Why Z chart? Because of the series, and since it's an inductor, the reactance is increasing, so we are going in the clockwise direction. So the two elements that we are looking at to transit from this point to this conjugate of the load impedance is this downward path of having a shunt C and a series L. Having a shunt C and a series L. The other configuration that is possible is to go up and down by having a shunt L from the source impedance. By having a shunt L, that means we are moving in the counterclockwise direction in the admittance chart first, hitting the other intersection point unlike the low pass filter case, and then having a series capacitor to go to ZL, all the way to ZL conjugate, to go to all the way to ZL conjugate. Again, we are starting from the source impedance, going along, having a shunt inductance in parallel and the series capacitance to go along a series capacitance to go along the constant resistance R equal to 1 curve to hit the ZL star. So this configuration leads to a high pass configuration where you're having a capacitor in series and an inductor in parallel. So both these configurations are possible. From the values of how much this jump in the susceptance in this case and the reactance in this case, we can determine the values of C and the L that is required in the particular matching network that we want to design.